Yeah, brand new laptop. Just couldn't handle it. Okay, recording's back on. Everyone's here. Sorry about that.
No problem. Okay, so so we were mentioning that we get this list of available survey property maps. So each of them corresponds to different observing conditions. For example, we have the average effect of differential chromatic diffraction, the PSF, we also have the limit magnitude, which is quite relevant when it comes to coordinate images, and we also have the exposure time, and this kind of sky background, this kind of different effects that we can take into account. We could also add to this list, although for these examples I haven't taken them into account, but we could also add other type of maps. For example, extinction from dust extinction from galactic dust, or any stellar density map, or any magnitude that you could imagine that could have an impact on the data. So once we have selected one of them, we need to ask to request it to the butler like this. And we need to specify the photometric band we are interested in, because each of them is available for each of the photometric bands. And then using the Hills parse formalism, it is quite convenient because it allows us to, for example, to get the values of the map at given positions in rate assumption and declination. Or we can also ask for a list of values of coordinates to obtain the values of the map at those coordinates. And it is also quite convenient that each survey property map is defined not on the full sky, but only over a region. So we can ask at which hill pixels they are defined, these maps are defined, and then evaluate the values precisely at those positions. So this is an example of how precisely the magnitude limit in I-band map looks like. So this is how it looks like, and you can see that there are some features and structures that can introduce artificial structure in the data, and that's precisely the kind of thing that we want to remove in, for example, a galaxy clustering analysis. So this is just another way of plotting these maps. This is adapting the color bar to have a better sense of how these variations are. And basically, this is everything I wanted to summarize from this notebook here. So this is a look at different observing conditions at the same time, together with a coordinate image. So it's a good start to have an idea of how to handle this kind of maps, and for sure it has been really useful to me in order to create my own notebook. So if there is any question about this one, I should pass maybe to the main notebook. So here is here are the different packages that I needed to run it. So the most particular ones are Hills parse, for example, as we have already said, different fitting functions from SciPy, and also sklearn to perform the PCA that we will talk about in a few minutes. And the rest of them are quite usual notebooks. So we initialize the butler with the same configuration as before, because we are going to work with the same survey property maps. So we start by displaying, as in the notebook before, one example of, for example, the Macklin survey property map. So we can start running this. And you will notice that I will refer to the end site in several parts of the notebook. So the end site gives the resolution of the pixels that form the hill pix map. And in particular, in Hills parse, there are two different end sites: the end site coverage, which corresponds to bigger pixels that contain the information of the subpixels with higher angular resolution. This is a huge resolution, angular resolution. I don't remember exactly to which angular size it corresponds, but it's really big. I mean, it's a really huge, a really big angular resolution. So as we are going to see in the next section. So first of all, we are going to plot again the cyber property map. Here it is. So we can see how it looks like the Maclean cyber property map in I-band. And after this, we are interested in order to better work with them, because one of the things I had to face during the creation of this map were memory problems, because I wasn't realizing that I was working all the time with this angular resolution. So that was a problem. Particular thank you, Douglas, for helping me with that. So we are going to set the end site to which we want to degrade this cyber property map. And with this simple function here, we can degrade it. Now we can make sure that the new end site sparse is 512. And now if we plot it, you can see that it's almost the same, but if you look closely at the edges, you can see that the resolution has decreased. For example, if we compare with this, this is almost a straight line, given the really fine angular resolution. But if we go to this lowest resolution, we start seeing some features. It's usual to see this kind of difference on the borders, unless the end site is really small, where you would start to see huge patches corresponding to the degrading of the high resolution patch pixels to lower resolution ones. Okay, so once we have done this, one of the main things that we are going to work with in this notebook, and one of the main tools that I have used during the DS galaxy clustering analysis, are what we call 1D relations. So these 1D relations basically are, they establish the relation between the observed galaxy number density of a given galaxy sample and the different values of the different observing conditions. So one of the first things that we want to look at when evaluating the contamination of different cyber property maps is precisely that quantity. So in this function that I define here allows us to define the bins of given the value distribution of a cyber property map. This function allows us to define bins of this distribution in such a way that we ensure that they cover equal areas on the footprint. So this is better seen if we just plot it. So this function here gives us, it's a hill sparse function, which provides us with the pixels where there are observations, where there are actual measurements. Then we can ask for the radic coordinates that correspond to the center of those pixels at the resolution we are working with. And then we can ask for the values at those pixel positions, at what we call valid peaks. And then these are simply basic checks to make sure that everything that the different outputs from this function make sense, so that we are obtaining the same number of valid pixels and the same number of values for those pixels and the same number of central coordinates. So once we have the values evaluated only on the regions that are actually observed, we can run the equal area bin edges function, and we can plot the distribution, the values distribution of this cyber property map, and the vertical lines here correspond to the edges of the different the different SP bins that we have defined. I have chosen to use 4 bins for the 1D relation. So that's why we see here 4 different regions, and you may realize that this one here is huge, and this is because these values here are not that representative of the survey property map. So they are quite extreme values. So we need to gather a lot of them in order to, we need to gather a wide range of these values in order to cover the same area on the sky. So now we can, to visualize this better, we can produce the corresponding HillSparse map with this tools from HillSparse. So we create an empty map. We initialize it with the end site coverage that we want, which is the same as the original, which was 32, and the hills and the same sparse site from the original map, which after degrading is 512. And then we update the values with the values of the different, with basically 4 different numbers, because that's the number of regions that we have decided to use. And this is how it looks like. So this scale here should be discrete instead of a continuum, but basically we are seeing the 4 different, these 2 different bins here, but projected on the sky, each of them covering the same area, even if they have this strange shapes. This would be great to see also on a stellar density map, because usually in these maps you find that there are gradients, because the closer you are to the galactic plane, the more stars you see. So these equal area regions would be represented, would be very well defined, because they change. There is a gradient on these regions as you get closer to the galactic disk. So once we have done this, we can load the rest of the survey property maps. So this is the list of maps available for each photometric band. We have 11. So this is just in case you want to run a quick test. And we are going to assign to each. Oh, can you hear me? Give me a second, because I have lost the. I need to stop sharing a moment. Settings. Can anyone confirm that that you can hear me?
Yes, we can definitely hear you.
Okay, I cannot hear any of you. I don't know why.
Oh.
Because my headphones had lost battery.
Oh, you might have to change your audio outputs things, but still headphones. Not that you.
Give me a second, please. Okay, I cannot hear any of you.
Where nobody's saying anything. Can you hear us yet?
Yeah, it's not on the, it's not in the settings, it's not, the headphones are not selected. Okay.
Headphones.
Okay, I can hear you now. I can hear you.
Okay, great.
I had to refresh it. Okay, sorry about that.
No, that's okay.
Okay. Okay, I stopped sharing, I think. Yes.
You did.
Okay, sorry.
We're back.
Okay.
Yeah.
Yeah, we're back again. So, okay, we were defining here a list of short names for each survey property map. This is just for convenience, because for plotting purposes, this is quite too long names for some of the plots that we are going to see. So we define a dictionary with short names for each of them. we are going to work with the I band, just to have an example. And this here in this cell, we would create a dictionary in which we store the different information of each of the subproperty maps. So we would request to the butler for them. We would degrade them to the desired inside resolution, in your case 512. And then we store this information. And we also ask for the valid pixels, that is for the pixels where the maps are defined. And we evaluate we get the values of the maps at those positions. Since this takes a few minutes, I have included in the repository a dictionary that already contains that information. So you can load it. And here, this is just a check to verify that all the maps that we are considering are defined in the exact same pixels. So we don't have to care about making a joint masking of them. And this is the structure that each of the entries of this dictionary has. So each entry of this dictionary is another dictionary with the information that we have stored, that the different sites, the valid pixels, and the values of the map at those pixels. Okay, so now one interesting thing that we can do with these maps is to compute the correlation between them, because the idea when correcting for the impact of observing conditions is we have to find a balance between having too many observing conditions, which is the same as having too many explanatory variables when you perform a fit. So most of the correction methods rely on fitting and assuming that the galaxy number density has a dependence, linear or not, of more complex functions with the values of the subproperty maps. And at the end, you want to fit that relation, correct for it, and you assume that the cosmological signal is the noise of that relation. But if you have too many maps, you risk to overfit because you can introduce too many variables to the fit. So one way of dealing with that is both to use methods that select the maps in a data-driven way, although that's another story. But the first step, one of the first things that we made in the analysis of GR3 was to have a look at the correlation between the maps, because some of them are going to be really correlated, if not 100% correlated or anti-correlated. So we can reject some maps based on the level of correlation they have beforehand, before running any method, and that also allows us to reduce the computing time and the computing resources that we need. So we can compute the Pearson correlation coefficient and obtain its matrix, but it's also a good idea to look at all the correlation coefficients. For example, the Spearman correlation coefficient. The point is that the Pearson's correlation coefficient assumes that the correlation between the random variables is linear, which cannot be the case. It's possible that's not the case between all pairs of subproperty maps. On the other hand, the Spearman's correlation coefficient assumes only that the correlation is given by a monotonic function, not necessarily a linear function. So if we compute both correlation coefficients and we find huge diversions between the values of them, we can address whether the correlation between the maps is really defined or characterized by a linear function or not. So we compute the correlation function with the Spearman's correlation coefficient, and now we can plot both functions to compare them. So this is the correlation for the Pearson's correlation coefficient, where you can see how correlated the different maps are. So you can see here this corresponds to the different subproperty maps. And you can see, for example, that this map here is very correlated. The number 3 is very correlated with, which is number 3, blah, blah, is this one. It's very correlated with this one, with the differential chromatic effect. And this way you can identify, if we do this with the full list of maps that is in the all, considering all the photometric bands, we can find families of maps and define in some way a threshold for this coefficient in order to reject maps or to reduce the number of them that we are considering. Looking at the Pearson's correlation coefficient, we can see that the differences between them are not precisely huge. So there are some differences. So there are some values that are smaller. It's not great to compare scrolling up and down. But if we look at if you look at the value numbers, you will find that they are not massively different. So this is an indication that the correlation between the maps is not perfectly linear, but is acceptable, or it depends to which extent you want to assume linearity later in your maps. So for the moment, we can assume that the correlation between these maps is linear, which is something completely different of these maps having a linear correlation with the data. We are talking now only about correlation between maps of different observing conditions. Another way that we apply to reduce the number of maps that we need to use at the end of the analysis is to perform a principal component analysis. So principal component analysis is basically in a geometrical way, from a geometrical point of view, is a rotation in the space of the random variables, in such a way that we select which directions explain most of the variance in the sample. So in this way, if we start with 11 survey property maps, we would obtain different linear combinations of these maps, which would result in 11 principal component maps. And if we order them, we can order them from explaining most of the variance to explaining only a bit of the variance. So using these functions here, we can have a look at the coefficients of the principal component analysis, and also the scree plot that I will see in a moment. So if we run this part here, we create a data frame containing the entries for each observing condition for each subproperty map. It is necessary to standardize the variables, that is, to subtract the mean and divide by the standard deviation of each subproperty map. And then we can have this table here with information. So by definition, what is called the PC1, the principal component 1, or simply the principal component, is that a linear combination of the original variables that explains most of the standard deviation. On the last column, you can see that as we increase in the number of principal components, we explain more and more of the cumulative variance until we reach, obviously, 1. So the idea is that the lowest principal components, lowest in number, explain most of the variance of the sample. In our case, of the set of, in our case now, the set of survey property maps that we are considering. It is possible to write this to a CSV file. And if we look at the scree plot, this here shows how much variance, not standard deviation, the variance, but they are just a square of the other, each principal component explains. So you can see the first one explains most of the variance. It's followed by this one. And then this is a way of deciding how many variables you want to retain. There are several criteria to make this selection. One of the criterion that is used is to try to find a turning point, a point of where the slope changes abruptly on this plot, to say, okay, we stop counting here from the lowest value to that point. But since this is not the case, or it's not that obvious in this case, there are other methods. For example, you can retain as many variables as they are necessary to explain a given percentage of variance. For example, we may want to explain 80% of the variance or 90%. So we would need to come here and see in which principal component we would need to stop in order to explain all that variance. There are different methods to perform this selection. For example, for TSGR3, we selected 98% of the variance after performing some tests varying this number. Okay, once we have that, we also, this package from scikit-learn provides this matrix in which each row of the matrix, for example, this one, or maybe I can show it here actually. So this is the first row. So these are the coefficients by which it is necessary to multiply each survey property map in order to obtain the first principal component. That is, the map PC1 is a linear combination of the 11 original survey property maps with these coefficients here. And it's useful to check, just to make sure that everything has gone well, that the sum of the squares of these coefficients, by definition of the standardized variables, has to be 1 or extremely close to 1 in this case. Now we can plot, we can initialize a new Hills-Sparse map with this random variable, so we can create in Hills-Sparse format the principal component maps. We have in this cell we choose to plot a few of them, the two lowest ones which explain most of the variance, and the two last ones which explain only a bit of the variance. So this is the first one, and you can see that if you compare this with the original plot, you will see that precisely one important component of the variance is given by the difference between the inner part of this square and the edges. So this principal component is capturing this variation, and you can see it in the contrast here between the values on the edges and the values in the inner side. This is the second one, where you can also see some kind of a gradient contribution to the variance, which would be the second feature that explains most of the variance in these maps. And these are the last two ones, which are more clear because they are more noisy, which are they show less structure that it's able to explain all the variance of on the set of survey property maps. Okay, so now we are going to have a look at the
Martín,
yeah,
just a question here.
yes,
The color bar is still labeled PSF maglim, which I think
sorry, that's
but it should be
PC1.
like PC1 and then PC2.
Good catch. Yes, that's a typo. I should have placed here. I will modify that. Yeah. So this would here correspond to the map values of the first principal component map. So this is the range of values.
Yeah.
This would correspond to the second one, and so on. And they can have, note that they can have negative values because they are precisely linear combinations of the original maps, which are given by these coefficients, which can be negative.
Yes, cool.
And the same for these ones. And they tend to be actually, they are centered around 0 precisely because of this and the standardization of the variables that we have to do at the beginning of the principal component. So we subtract the mean, and they are centered around that.
That makes sense. So we could even just replace that label with what you print out at the top there.
Yeah.
I think that's probably the easiest, yeah.
Okay, actually I can, if you want, I can do it on the fly actually. Okay, this is going to be better. Okay. This is what happens when you copy paste different parts of the code. So thank you so much. Okay, so these are the, as we were seeing, so these are the different principal component maps, and we have 11 of them. So note that I should actually, I'm gonna leave it running there, but I'm going to place here class 1 because we named them that way. Okay. They should appear. Okay, cool. So if we will have always the same number of principal component maps as the number of maps that we originally have. So it is essentially a change of base. Okay. Is there any other question about this part? May I continue? Okay. So now we are going to look at the impact of these different maps on the data. And for this purpose, we are going to use galaxies from the object object catalog, particularly from the simulation. And the first thing we need to do is to translate from coordinates to pixels for the resolution we are working with. So we define this. We have previously saved the columns that we are interested in from this object catalog, and it is saved in a pickle file which is in this directory. So you should have access to it. And basically, this function here is going to use the radect that we select from this file here. Sorry, from this file. Here is the file. Here is the table for the file. So this is basically a selection of columns of from this object file. And we are going to select. I have decided to use this flag here to select galaxies. So I set it to 1 in order to have a selection of galaxies from that list, from that table. Then we select which coordinates correspond to that flag. We print simply how many objects we have. So we have quite a bunch of them, and this is the range of rate ascension and declination that they cover. And then we give these coordinates and the n side, remember 512, to the function that we have defined above, which basically transforms using the HillPy functions, transform each coordinate, its radix coordinate, which are internally transformed to theta and pi, to pixels. And then for every single galaxy for which and that lies in each pixel, we add one more to that pixel, basically. So we have for each pixel, this resolution and the degraded resolution, how many galaxies are lying in that pixel. So this is just to check that we have selected that the function has returned the correct number of objects. And this is the distribution of values. So this is the number of galaxies and how many pixels there are with each of the values using the output from this function. And we can, using Hill's parse again, produce a map of the different of the galaxies that we have selected. Okay. So this is just to confirm that we are observing the same, that we get the correct number of galaxies. And now we are going to plot this, to make this plot here. So what we are doing here is essentially to to evaluate the galaxy, given the Macklin map at the same positions where we have galaxies. So we are effectively applying an angular mask. So we are selecting which pixels from the observing conditions are in correspondence with the observed regions in the catalog, in the galaxy sample that we are interested in. Now we can mask all the subject property maps that we are using to be evaluated only on these regions. Again, you will need to run this cell here in order to create a dictionary that saves the information for only those regions here. But in order to save time, I have included it on the repository, so we can directly load it. And now we can compute the 1D relations that I have talked about at the beginning. So,
sorry, Martín, I have
yes.
another question. It was saying, we previously saved the columns that we were interested in, but I think, did you do that in a different notebook?
Yes. So this was something I asked CV some help with. So because
so yes, for this, I use the tab system to request for a number of sources in this region. And the point is that I have requested a limited number of I have put a maximum of, I don't know, 5,000 objects.
50,000.
So because, okay, I wouldn't overload the tab system, but I think that is why there are some holes.
Yeah,
and
that's what I was...
probably we should build a better, but we can do this later, a better, let's say, to load more object, perhaps patch by patch, or you see, I have truncated abruptly the sample.
Yeah, that's what I was wondering. It looks like a tap search with no region constraints, and that you've only...
Yes, it's this whole region,
Mhm.
but and there was no selection on the magnitude. I don't know if you have added this, Martin, but okay, we should produce a better pre-digested object summaries.
That,
Yes,
or just add some text telling the user what the query was that you did and why the map looks that way. I wasn't trying to say it's fine to have these gaps. It's just users won't know what search you did.
Yeah.
That's all. Yeah.
Okay, great. Yes, so the main requirement for the selection was that they were lying within the same angular range, or angular range in right ascension and declination as the subject property maps, in order to be able to make the match with them. That's what the only requirement. So so we can include that. Yes. So it was just for this purpose. It really didn't matter to have this non-contiguous regions. So, but yes, we should definitely add that to the information of the notebook.
Yeah, just so users know what the query was and that it's patchy because you requested only 500,000 galaxies. So it went through, when it does the search, it uses the tables that are set up by area. So it'll get you the first 500,000 in whichever patches that it goes through. That's all. Yeah.
Okay.
Yeah.
Okay. Great. Okay. So so we have evaluated the map, each of the maps on the same region than this selection of galaxies. And now we can compute the 1D relations for each of these. So this function here returns the coordinates of these 1D relations of these blocks on this slide. So this is better seen with the plotting in front of us, but it takes as arguments the galaxy, the map of galaxies that we are interested in. The mask is basically the valid pixels where this galaxy sample is observed. That is these regions here. The list of pixels were corresponding to those pixels, and the values of the survey property map, and how many bins do we want to do to this to calculate this this 1D relation. And basically, it computes what it does is for each bin of observing condition, it evaluates the number of galaxies that are on that patch on the sky for that bin of observing condition, and it compares it with the number of galaxies in the full footprint. So I will come to this function later, and we can plot an example quick easily. So we select 10 bins for the 1D relations. We run the function here, given the number of galaxies, the mask, and one of the survey property maps as an example. And here it is. So this is the the 1D relation corresponding to this differential chromatic map, and basically it gives us the how is the number of galaxies compared to the number on the on that part of the sky compared to the number of galaxies that in average is observed in the full footprint. So you can see that for the most extreme values of this map, there is a deficit of galaxies compared to other regions. So the blue line, the line equals 1, would give us basically that this map has no impact on the data. If we found something completely flat or that compatible within the error bars with the blue line, that would be telling us that that map has almost no impact on the data. We will find the same trend independently, the same number of galaxies independently of the values of the observing condition. By the way, these error bars here are calculated simply as the inverse, as the standard deviation of the data on that particular bin, of the number of galaxies in that particular bin, divided by the number of pixels corresponding to that bin. And the number of pixels corresponding to that bin is roughly the same for all 1D bins because of the way we have defined these regions, because they cover the same area, basically. So we can compute this for all survey property maps. Now we create a dictionary containing information for each of them. This is just a reminder of how many maps do we have. And now we can compute the 1D relation for each of them. So this is how the 11 maps, the 1D relation of the 11 maps looks like. So you can see that there are different levels of contamination. So each of them has different amplitude of the impacts, also depending on the 1D bin that we are looking at. For example, this one here, the exposure time, has a remarkable impact, which makes sense because it's basically telling us that we are for the regions where we have observed less time, we have less galaxies, which makes sense. And that correlation goes up. For example, we could also see where is the sync maps. For example, the limit magnitude also shows a positive trend, which also makes sense because the less deep we are, the less galaxies we see. And in these plots, the purple line corresponds to the fit of the red line of the 1D distribution to a quadratic function. Why have I decided to do this fit? Well, in principle, we could use any type of function. For DSGR3, we used only linear functions or a version of the linear functions. But for this case, I found it more interesting to play with a second order polynomial. So why do we want to fit this? Because we want to correct for this effect by fitting these 1D functions and obtaining from them a weight map. So how do we obtain this weight map? What we do is to, what we do is to obtain the fit of each 1D relation, and then we obtain a weight map as the inverse of that function that with the coefficients that we have obtained from the fit evaluated on the weight on the survey property map that we want to weight. That is, in summary, we obtain from this 1D relation for a given survey property map the coefficients of the fit. So we have defined a function, and then the pixel values, we can evaluate the inverse of that function on the pixel values of the corresponding survey property map. So we define that way a quantity, a pixel map, which contains in each pixel the inverse of this function evaluated at the corresponding pixel on the survey property map. And then we can plot so we have, I took as an example, why is this happening?
You missed some cell above.
Thank you. So we run this. So here we are selecting the coefficients of the fit. And this is the distribution of so I have selected as an example the exposure time. And this is the distribution of the weights corresponding to it. So as you can see, they are around 1. It's not centered around 1. And this is because this is the shape of this distribution for the weights is going to depend on the shape of the distribution of values of the corresponding observing condition map. And if that map has important tails or it's very skewed, that's going to be translated into the weights. And that's clearly seen also here on the 1D relation. So in order to compensate these loss of galaxies here, you have to apply a bigger weight than for regions here. So if this 1D relation is very skewed because of the distribution of the survey property map values, that's going to be translated into this distribution of the weights. And now we can apply the weight to the galaxy sample by simply multiplying by this weight map. So we multiply the values of the number galaxy values by the weight map with the idea of correcting for that effect. To evaluate, to check whether we have corrected for that effect, we reevaluate the 1D relation of the weighted data, so that is N-gal W, with respect to the same survey property map. We load the 1D coordinates, and here you can see, so this was the original 1D relation in red for the raw data for the galaxies with no correction, and in blue you can see that we are able to make the 1D relation compatible with the null line, with the line equals 1, which tells us that this is now compatible with no effect. So in order to do this, I have selected just by eye one of the maps, but we would need to define some way of saying, okay, this is the map we have to correct for, or we don't need to correct for this map because it is compatible with no effect. For example, we could consider that here for this PSF map, we could consider that it has no significant impact on the data. So that's the purpose of the different correction methods. So that's beyond what we wanted to present. But for example, what we did in the DSGR3 was to apply different methods that work on these 1D relations, and they decide by looking directly on the data which maps are the ones with the highest impact, and then corrects for them if not exactly in this same way, in a similar way, that is obtaining a weight map that is applied multiplicatively to the data, and then we can later, after applying them, verify that we have removed the effect. And that was more or less everything I wanted to show with this notebook. So if you have any question, please go ahead.
Thank you very much.
Yeah, thanks. Thanks, Martín. Does anyone else have any questions? You can unmute, you can raise your hand, you can put it in the Zoom. Nevin?
It's not directly connected, but I'm interested when you were showing this, it might be more Melissa, how the 500,000, the patches were like almost random. How does that work? It's just because how it's laid out in memory, or why is it such an interesting structure? Yeah, here.
Yeah. Well, here, right, I guess. I guess it's just because it was the way the only constraint that was placed on the query was that they lied within this region, and we didn't care about the order. They were red. Right. And in addition to that, it was set this limit of 50,000 galaxies. So when it reached that point, it stopped.
What I'm interested in, how, let's put it, it's random in my mind. How does it? Why does it look how it looks? Is that just memory, or like how is it laid down in the database, or what first gets to it, or?
Exactly. I think it's just how it's partitioned in the memory and how the service starts going through the
right, which is almost random, basically, hopefully.
Yeah. What I'm not sure is if you just like redid your tap query,
yes,
if like the boxes would switch, or if it's because of how it's laid out in memory, if it kind of goes through the same, like, I'm not sure exactly how.
That's kind of interesting. Yeah, thank you.
But
by the way, we can ask for which number of object at maximum in a single query. Perhaps because it was done in a notebook, so probably you cannot request a lot. Or perhaps there is some way to make a request outside a logbook in all this.
It shouldn't matter. We have some other notebooks that are doing like 10 million stars.
10 million. Okay.
Yeah, that's notebook, I think number 6 or 6A or 6B. It gets like somewhere around 10 million stars, and then it's using data shader to plot them. So I think like 10 million, especially if you are only getting a couple of, like you only wanted RA and DEC, right? You're not just 10 million coordinates. It's not like you're getting all of the columns. Yeah, so try for more and see.
Yes, we will do that.
Yeah, I can update the notebook reading a more populated version of this to get more interesting results.
Yes.
Yeah, I had one question, but I think I may have just missed it at the start, which was just some examples of science applications of this. Like what kind of cosmology do you apply it to? Does this fold into like commissioning efforts as well, or what do you do with it?
So you mean with the usage of the subproperty maps, or with the developing of the technique, the correction technique? Sorry, I'm not sure I
like you're applying it to some cosmological studies. Are you doing weak lensing? Are you doing?
Yeah, exactly. So the main part of all the philosophy behind this was developed for the galaxy clustering analysis for GR3 of DS. So in particular for galaxy clustering, or in any case to be applied to any sample of galaxies that was going to be used as lenses. So for weak lensing, for galaxy lensing, this was also crucial. So basically, we produced we were given a galaxy sample of lenses, and we returned the same sample with a column of the weight in the systematic weight associated to the observing condition for each galaxy. So you have to apply that weight or you have to take into account that each galaxy counts as the value of that weight when you calculate the 2-point angular correlation function.
Okay, I see. Yeah, that makes that makes sense. I'm sorry if you said that at the start. I just
No, I wouldn't. I just said that. I don't remember actually. I don't think I said it.
Okay. Yeah. Yeah, cool.
I can
Anybody
ask
else?
another naive question.
Do it.
So I see these consolidated maps. Those are just available. They were produced by LSST, or how does that work? The ones which you were loading at the beginning in Butler. Like you printed at one point all the consolidated maps
Yes.
that you can get.
Yeah, it was here. Yes. This list, right?
Right. Like where does that kind of come from?
Honestly, I'm not sure.
Right.
So yes, it is somewhere in the pipeline, LSST Rubin
Okay,
pipeline. At some stage, after the early stages, I have seen it could be done. What is the name of the standard pipeline? In DM software, I don't remember.
Right.
The data release
DP
pipeline?
pipe, something like that.
Right.
And
Okay. It's produced as a part of the pipeline, and it's available in the Butler when you load it in.
Yes.
Got it.
Yep, they're there, and I'll note too that we do have in our documentation like lists of available data products. We don't list the consolidated maps in there, not for any reason. We just sort of think most people will be using images and catalogs for DP0.2, so they're not listed anywhere. But the tutorial notebook 03C was made by Eli Rykoff to try to advertise the fact that these do exist. So we should add them to our documentation because it is like a useful data product that people want to use. So I'm going to make a note about that because they're not.
And it looks great.
And yeah, they're useful. They look great. They're fun. Oh yeah, there we go. So that's the only place right now. It's just 03, the notebook 03C
Yeah.
in our tutorial.
Got it. Thank you. Thank you.
We should put it in the documentation. Yeah. Okay, any other questions for Martín today? Okay, in that case, thank you, Martín. Round of applause. Yes.
My pleasure.
Yep, pretty fun. And we will we'll go to breakouts if people would like to do some breakout sessions. So let me just pull up my slide that we use to define breakout rooms and go ahead and suggest a breakout room in the chat or unmute.
If anybody'd like to go over my regression analysis that I just wrote with me, I'd appreciate it.
Okay.
I'd like to see that.
That'd be great.
Okay, cool. So we'll make a room for you guys to work on that for sure. Oh, my chat closed when I started screen sharing.
If anybody wants to know more about the survey property maps or how of these methods, I'm happy to be in a breakout room also.
Yeah, anyone else for more? Oh, looks like people have to leave for the second hour, which is fine. Does anyone want to do an intensive on survey property maps?
Is it possible to perhaps, sorry, I'm sick, to perhaps do this again, pick this up again? Because I'm also having a similar time conflict, but I think it's very valuable. I'm just, yeah, hoping it's a possibility.
To do what again?
I'm sorry to pick up the survey maps and then an in-depth exploration of these, but perhaps at another time. Or is that completely unfeasible?
No, that's kind of what Stat Club is for as well.
Okay.
So next Friday, if you show up, maybe there'll be other people there who want to do that kind of thing during Stat Club. If you can't say no.
Yeah, I'd definitely be in it for next week or whenever to hear more about the survey property maps.
Yeah. Maybe is it something that we could just suggest just to give people a heads up and maybe even get more attendees and then yeah, I'd love to do it next Friday. Yeah, just but hopefully getting a little more organization / attendance. Is it a Slack thing that I write or is how do you?
Oh, no, Stat Club is entirely drop-in, and then
Oh,
whatever
nice.
happens during Stat Club is what the people who show up want to work on. So it's very, very disorganized on purpose. It's so
No,
It's the same
Yeah,
Zoom
yeah.
address, just connecting the same way,
Yeah.
same place, same
Yeah.
time too.
Yeah, and I would love to do that. I think it's nice to have Martín participate in this too, since he has the keys and the answers. Yeah, I know, I agree. The whole principle is very drop-in, but since I'm like requesting a particular thing, that's why I'm like, oh, can we organize it? But yeah, maybe I'll have to just cross fingers.
Yeah, this is the time for that kind of thing. So perhaps 2 weeks from now, a pre-organized breakout, even though we try to do those on the fly as well. Yeah.
Okay, thanks.
Okay, so
I mean, I wish that Vincenzo was here. I worked on his notebook showing how to extract supernova.
yeah, Vincenzo's presenting November 18th. He's
Oh,
gonna be
lovely. Okay,
presenting, so
great.
you'll
Okay, let's
get
not
lots
do
of
that.
Vincenzo that day.
Okay. Okay.
Yeah. And he's often appears at Stat Club as well. It's a place to drop in. Okay, so I think today we'll just be doing the one breakout room, and then we'll stay in the main room to answer general questions. And then if anyone else is staying in the main room to work on survey property maps. Martín, do we have you for another like 30 minutes or so?
Yeah, sure.
Okay, yeah, so main room can be general Q&A. And Martín can answer more questions here, and then we'll just make one. We'll always make two, so we have an extra just in case. Stopping recording, we don't need that anymore.